So yeah, as introduced Sam, my background is as a geologist and in remote sensing. So today I'm going to take you through sort of some understanding of remote sensing and then how we're applying that to sort of a relatively challenging terrain. I think a lot of the times you look at remote sensing for really open, great exposed areas, and sometimes or quite a lot of the time, we have people come to us looking for quite challenging terrains and with very minimal exposure. And so here we're going to go through an example over the Gawler Ranges today. That's not moving forward. Probably lag. There we go. So sorry to the remote sensors in the room. We're going to go through a few basic concepts so that we're all on the same page. Quite used to working with geologists who maybe never have looked at the satellite picture. So we'll go through that, get some terminology, and then we'll go from there. So we are looking at optical data here. We're looking at where the sun has shined on the surface, and then whatever composition at surface has absorbed certain wavelengths of light. And then we're detecting the light that is then reflected back up at the satellite. So it's what optical remote sensing is really about. Key wavelengths of light we're going to be looking at primarily in the visible to near infrared and into the shortwave infrared for remote sensing. We're looking in the thermal quite a lot as well. But for the purposes of today, we're really going to be focusing in the visible to near infrared and shortwave infrared. It's where a lot of the optical sensors are collecting at the moment. Some key terminology that we're going to want to look at are spatial resolution. So that is really the size of our pixel that we're looking at. You can sort of see here, we're looking at a city landscape, and you can see that as the resolution increases, we're going to be able to see more detail. So at that 1 meter, it's pretty obvious what we're looking at. As we move to the 10, you could roughly pick out what we're looking at here. 30 is going to be a bit more challenging to really look at anything. And then 250, we're struggling to see very much there. So having an understanding of what we're looking at is pretty important. So maybe see like a building as a big prop, and then we can sort of work with it. Spectral resolution is really important. So if we think about our spectral resolution as points on a graph, or the wavelengths of light that we're looking at, the number of points, or the larger our spectral resolution is, then the more we're going to be able to discern. You can sort of see in the top left, or the image in the middle here, this is a laboratory spectra. So it's got sort of 2,000 points on this graph that we're looking at. We can discern quite a lot in terms of the different shapes that we're picking out here, and from that we can tell more about the composition of what we're looking at. More on that in a bit. But as we move to some of these different satellite sensors, so it's these exact same spectral signatures, but resampled to the number of wavelengths of light, and the zones of those wavelengths are collected at 4 different sensors. Landsat, ASTER, WorldView you may be familiar with. And sort of, as you can see there, as we get to ASTER, which has 9 spectral bands across the visible and shortwave infrared, you can see some of these absorption features being picked out, but they're not characteristic. They're not going to tell me exactly what we're looking at. And this is one of the limitations with multispectral data, which I'll define in a second. And we're what we can say is determining what our mineral groups are, but we can't determine what our mineral species are. And that's really where the importance between multispectral and hyperspectral comes in. So multispectral, you can sort of see along the bottom here are tens of bands, really. This fused is something that EarthDaily uses quite a lot. It's a combination of Sentinel-2 and ASTER data, which are 2 of the sort of most common satellites that you use in mineral exploration for, really the last 20 years. And you can see how many wavelengths of light they're capturing, right? So 15 in total, 9 in the shortwave infrared. 9 in the shortwave infrared and 9 in the visible to near infrared and 6 in the shortwave. EnMAP which I'll talk about in more detail in a minute, is one of our new hyperspectral satellites. And this has 246 spectral bands. So that increase from 15 to 246 is going to mean that we can determine more from our spectral signatures when we're looking at those. And why is this important? And why are we looking at these wavelengths of light? Then, certain materials have key diagnostic absorption features at certain wavelengths. And so you can sort of see along the top here, very general categories for the sort of minerals that we can pick out. So in our visible to near infrared, this is where we're seeing a lot of iron oxides. We can see rare earths there, but it's also where we see vegetation, which can cause some issues. And at the far end, we can see some of the thermal data is where we see a lot of sort of non-OH bearing silicates. So think of your quartzes, your feldspars. And then as we go sort of in the middle is a sweet spot for a lot of hydrothermal minerals. So your white micas, your clays, your phyllosilicates will all be forming there. And so, this is why when we're thinking about sensor design, we're targeting these sort of wavelengths of light. Now, as I said earlier, the focus of today, I'm going to look at the visible to near infrared and shortwave infrared. So just to get you thinking of the types of minerals that we can target in this range, then this is really where we're going to focus, because that is where the majority of these new sensors are looking, in the visible to near infrared and shortwave infrared. And I don't think I have to say to a room of geologists the types of deposit that we can look for and the types of metals that we can look at. I'm often showing this to non-geologists who want to know why it's important that we're looking for these deposit types. But in terms of the remote sensing, we're looking at for these potential deposits. Now, are we ever looking for gold specifically or copper specifically? There's no signature that's going to be diagnostic in these wavelengths of light. We're looking for proxies. We're looking for minerals that we're trying to target there. Now, where can spectral geology be done? I'm sure most of you have crossed paths with this at some point, but it really is from satellite down to subsurface, right? Everything from airborne, drone, field in between. And for the purpose of today's talk, I'm going to focus just on the far left end, right? We're going to look at more regional scale satellite and airborne data sets, but we can move down and think ahead that we can also incorporate drone data, field data, and then move into our drill core, or work the complete opposite direction as well. So we can work out from known drill core and then look at where we can see it in our satellite data too. And typically, generally, as we move from left to right here, we're going to be increasing in our spatial resolution. So the pixel size is going to be, much smaller. Sometimes there's differences there, but in general, that's going to be the case. So I think it's worth putting in perspective what satellites have been out there and made available in the past, and your sort of typical workflows with multispectral imagery in the satellite space are on the left. So ASTER, Sentinel-2, Landsat missions, WorldView 3. I'm sure a lot of you have crossed paths with this in the past. And those spatial resolutions can vary depending on the sensor, right? But the best ones are going down to 10 meters in the publicly available, and then in the commercial can go down to even 30 centimeters. So some really high resolutions there. And then airborne, we can see similar impacts there. Now, is there a perfect sensor for all of these? Absolutely not. You can sort of see here that as I highlight different sensors, they all have different benefits in various wavelengths of light or spatial resolutions that we're targeting. So we have to have a real understanding of what sensors are out there and available before we can implement it in an area that we're trying to target. How do we then take that? It's important to put into perspective what you're trying to do, right? So we could be looking at a real regional scale. And so something like the ASTER data at the top there is going to be a reasonable resolution at 30 meters, because we use this rule roughly called the 1 to 2000 rule. So if you divide your sort of spatial resolution or the scale you want to map at, divide it by 2000, you're roughly going to get the spatial resolution of the sensor that you might need as a starting point, right? And as you move down, you can see the need to move to these different sensors there. Now, scale is one thing to look at, but we also need to think about data coverage. Some of these sensors are collecting globally. Most of the satellite sensors are. Not all of them are collecting all the time. You have to task it. That takes time and can be considerably challenging in areas where the weather is hard to capture a cloud-free image. You also, if you're looking at airborne or drone surveys, they're challenging going to have to send someone out there, and that can be time-consuming as well. And they can be costly. And we want to use ultimately the best open source data available first, and then grow out from there and see if you need more expensive surveys. And I think I'll hark back to that at the end of the presentation as well. So what new satellites are out there and what are we using now? Here you can see sort of a timeline of existing missions and missions to come. Along the top here, you can sort of see two on the top left. Hyperion was launched in 2000 and was sort of way ahead of its time, theoretically, but the issue is that it had such bad signal to noise, so it was such noisy imagery that it was really challenging to actually interpret the data, and so it essentially became pretty non-usable. And then we moved to DESIS, which is on the International Space Station, but that's not publicly available. It's only really for research purposes and something that we can't access commercially. But then in the last sort of 5 years, we've had 3 different satellites that have been launched by the Italian Space Agency, the German Space Agency, and NASA, which is PRISMA, EnMAP, and EMIT, which are 3 hyperspectral missions that are really have pushed the boundaries of what we've been able to do in mineral exploration space. And this is just the beginning. There's more to come. Maybe the SPG is being cancelled, but there's more opportunities that are coming down the pipe for future hyperspectral missions. So we want to understand how we can work with this data and how we can really process this. And you can see here, they're generally a similar spatial resolution. So PRISMA and EnMAP are 30 meters. So if we compare that to some of the other sensors we were looking at previously, then ASTER is also 30 meters. So we've got a good comparison there, pixel by pixel. And then we've got some EMIT at 60 meters, which is much more regional, but is still very, very valuable in terms of the composition, because the benefit of this is that it can cover much larger areas. So we have a big archive of these data sets to be able to utilize. Now, that's just the publicly available data sets. We need to also be thinking that there are commercial companies that are launching new satellites that have hyperspectral opportunities as well. So listed here are a few of them. The top 3 have all since launched their satellites. I'm still trying to get a hold of some of their sample data, so fingers crossed I can take a look at that. But you can see there, compared to the public data sets, we've got an increased spatial resolution on one of them. And then the other benefit for Planet is that they can actually task that satellite. So we're not in control of where these sensors task necessarily, or we don't have priority on tasking for some of these sensors from a commercial perspective. Whereas for some of these commercial satellites, then we're able to task those actively. And then there's more to come, right? So we need to know what the potential is of these different sensors and how they may be valuable for our exploration practices. So now to actually get into the remote sensing side of things. I'm going to be looking at the Gawler Ranges today, and a lot of this is actually built out from Alicia Caruso's work that she did for her PhD, who is at the South Australia Geological Survey. And what we're building off is looking to see how comparable EnMAP data is to some of the airborne hyperspectral data sets that were flown here. A HiMAP hyperspectral data set was flown here, so we want to be looking for how they compare. Now, it is a the geology here is Paleoproterozoic in the basement units, where we can see some potential porphyry and epithermal systems take place at surface. Now, you can see a couple of the sort of exposures taking place here, which are not particularly large, but is in a highly regolith-dominated terrain. And so regolith can often have challenges when we're actually mapping that with satellite data, because it can form a lot of false positives from whatever it's eroding out from, but can also, cause us to have a lack of exposure for the geology that we're looking at. You can see here that there's been some work on ground truthing this. There's a lot of alunite present, dykite, kaolinite, barophyllite, sort of key alteration minerals associated with a porphyry copper system or epithermal system. And they're the sort of things that we're going to want to be targeting with our hyperspectral data here. We're going to want to take a look at that in a little bit more detail, and I'll explain some of the different sensors that we're going to be looking at here. So what I used in this study was our fused bare earth composite data. Now, this is something that we, as I mentioned earlier, is something that EarthDaily has that's proprietary. It's a combination of that Sentinel-2 and ASTER data. So found that we've gone through the entire archive that's available and found the optimum pixel. It's often challenging when you come to some of these terrains and you've got a lot of cloud in your imagery, you've got shadows, you've got dense vegetation. It's at the wrong time of year where there may have been flooding. And so what we've done is found the optimum pixel with that lowest cloud, lowest vegetation, lowest shadow, water, all of these factors that we're going to want to avoid, and found one global seamless composite. So it makes my job really easy because I don't have to worry about where I'm getting my data from too much to start off with, and it means that I can really focus in on doing the analysis from the spectral side. As you see here, we're looking at varied resolutions of 10 to up to 30 meters. Which is relatively comparable to the Nmap sensor. So that hyperspectral satellite imagery that we're going to be looking at and was collected, the scene that I ingested was collected in April last year. So pretty good time to be collecting data in South Australia. This is all freely available from the German Space Agency, so it's great that we can access that and analyze that. And you can see those number of bands at different wavelengths, you can see. And then we're also, I downloaded some of the HiMap airborne hyperspectral data from SARIG, so South Australia's resource gateway. And there has been some vegetation masking that's been applied. We'll come back to that as a sort of limitation later on, but just for your sense of awareness, it's important to understand any pre-processing that's been applied to a data set like that before you analyze it, because it could mean that you'll have some limitations going on. But you can see here, we're jumping from 30 meters down to 4.6 meters here in our spatial resolution. So almost an order of magnitude increase there. And so it'll be a really good data set to be able to compare what the capabilities are of the two hyperspectral systems. So how did I actually process this? And this is my one plug of the evening. We have a tool called Marigold, which essentially makes remote sensing incredibly easy for anyone who is a remote sensor through to a geologist who's never looked at remote sensing imagery before. It makes it very simple to generate different band ratios, mineral indices, and spectral processes, and be able to do that at a global scale. So, a lot of the challenges that you have when you're working with remote sensing data is the pre-processing and the data access. That's probably the biggest amount of time that you're looking at the data, and so we've tried to remove that from the conversation, because you're able to just start processing and the data is analysis ready for you. The other challenge is some of the hyperspectral data sets are absolutely ginormous, and so it can take a long time to process. Our interface is backed up by the AWS supercompute, so we're able to process things much more quickly, and I'll give you an example of that in a moment. A little bit of background, probably don't need to explain this too much in this room, but we're looking at trying to identify alteration styles as part of a porphyry and epithermal system here. Typically in the shortwave infrared, you can see a number of different minerals here that we can target in those alteration zones. If we go back to looking at the geology that was mentioned earlier, the kaolinites, dickites, aluniites, pyrophilites, they're all things that have been noted in the field to have been observed here. So it's great for us to be able to look and target some of these advanced argillic minerals and be able to look at those. So that's really the aim of this, to be able to see what those capabilities are. So now to move into the hyperspectral processing, I think the goal for me when I'm starting to look at a new area is find the best example of a spectral end member, right? And what is that really? We're looking for the best example of a spectral signature of a certain mineral that I'm going to want to target. And we'll work through how we can do that. There's a number of different directions we can do. We can go down to explore that. So we can start with the multispectral processing. I think it's worth understanding what we could do in the past and what's now capable with the data. So one of the first things we're going to want to do is mask out any potential false positives. One of the things we mentioned at the start was vegetation. There's quite a lot of vegetation in this area. And you can see in green one of the vegetation masks that I generated here. And then we can remove that from the imagery. It does seem like a lot of data we're sort of losing, but unfortunately that's just the nature of working with only things that we can see at surface and what we can see from space. And what we're ultimately, it's a good thing because it's going to reduce potential false positives that we see further down the line. So we're going to want to remove those where possible. A lot of, if you have worked with remote sensing data in the past or been delivered results, then you may have seen sort of band ratios and mineral indices that look similar to what we have here. They're really just simple calculations, well, some more simple than others, looking to target certain absorption features at different wavelengths of light. So all of these are targeting some of those hydrothermal minerals. The ALOH band 5 in the top left there is really can highlight minerals like alunite, pyrophilite, kaolinite, dicite, and the same goes for the alteration. ALOH band 6 can highlight muscovite, illite, smectite, montmorillonite, kaolinites, dickites. You can see there's a bit of overlap here, and the same goes for KLI. It's quite a generalist index. Now, we can see that although they're meant to or can highlight different things, you can actually see that they are highlighting quite different areas, some more subtly different than others. I think that the most distinct is between sort of alteration and the ALOH band 6 indices there. So, we can start to see that there is compositional variability that we can pick out in this area with the multispectral data. So how can we look at that in a bit more detail? We can actually make what's called a ternary image. So you can see here in this diagram I've put together that we can combine 3 of those indices that we just showed in a single output. And that allows us to interpret these in correlation with each other. So you can start to see those areas in red where just the ALOH band 6 is. We can see the areas in green where just the alteration is. Areas in yellow where we have a combination of those, red plus green is looking at yellow in this color plot, and then those areas in blue where we maybe just see that KLI index. So, as a geologist potentially going into this area, we've got a few places that we could visit and look and see some differences there. But could I tell you with confidence that this was looking at argillic alteration styles or know what specific minerals we were looking at? No. So this is really where one of the limitations of multispectral data is, because I can tell you there's certain mineral groups here, but I can't tell you the specific mineral that we're targeting. So how can we take this and use our hyperspectral data? There's a couple of different avenues. As an initial starting point, what we can do is actually take spectral library files of known spectral data sets and apply those to what we're looking at. To work through this very quickly, this is where we're learning some very brief spectral geology. Here are 4 of those key minerals that were are known to have occurred over this area that we can target. Porphyry in the top left has this really sharp absorption feature at 2165. Alunite below this has an absorption feature at the exact same place, but is much wider, has this broader absorption that you can pick out there. And that's really how you can tell the key difference between those two. And then you'll see kaolinite and dykite. They're polymorphs of each other. So they have very similar spectral signatures. They have this sort of doublet signature that you can see. For kaolinite, it's 2165 and 2207. And then for dykite, you can see that actually there's a very subtle difference where the absorption features are slightly narrower. And this has been observed in a number of different locations geologically. So it's quite a nice way to be able to differentiate. I may test you on some of these going forward. So what we can do is say, okay, well, I've got this pyrophyllite signature. I want to look for where I can target that. So I can start with a pretty simple classification, a spectral correlation macro classification I'm going to use throughout this. And essentially, it's saying I've got this input spectral signature. I'd like to find in my Nmap hyperspectral data now where I can see similar spectral signatures to this, and then provide me with a percentage match of this. Now, this is a really good classification compared to some other classifications out there, because it takes into account both the negative and positive correlation of the input spectra that we're taking there. So we can do that for all of these different outputs, and now we can start to see that there's a bit more subtlety in what we can see and pick out there. The porphyry that we're seeing here is mainly just in two locations in the top left. We're seeing a single location for alunite to be picked out. And then for the kaolinite and dykite, we're seeing pretty similar responses. Now, they are polymorphs of each other, so they are going to be very, very similar, and there may be subtle differences that we can pick out there. But I think it's really important for us to know, and for anyone who's looking at remote sensing for a start place, this is not the best place to finish, right? You can't just put in the signatures from the USGS spectral library and be done, because you're going to get potential false positives where there's overlap between these mineral compositions. And so it's much... It's really crucial to be able to interrogate the data spectrally and actually understand what we're looking at there. So, as I said earlier, this is where we now want to look and analyze those spectra and find that spectrally pure signature, which I don't really like as a term, but because it's very rarely a pure signature, as you'll see in a minute. But it's sort of the best example that we can find within the imagery that's going to give us confidence in what we're looking at. So how do we do that? I've got the multispectral output, one of those multispectral outputs, the ALOH band 5 index here, and then one of those alunite signatures that we pulled from the USGS. So we've got multispectral and hyperspectral here. And what we're going to do is zoom in on this one area, which is Ni-Cu-PGEs Hill. And you can see here, actually, they're not, the multispectral is not doing a bad job, right? It's picking out the same location as the alunite signature here. There's a few other areas that are being picked out. We'll come back to that in a moment. So what we can do is start to interrogate that imagery. Now, if I was to look at just the fused data here, this is the sort of signature that I would get. If I picked from that pixel here, this is the spectral signature that I have. So I've got an absorption at 2165 taking place here, but that could be alunite being present, or that could be pyrophyllite, that could be kaolinite, that could be dykite. All of these minerals could cause an absorption feature like this, unfortunately, as well as a mixture of any of those minerals combined. So at this point in time, I'm not confident in saying that is a specific mineral that we're looking at there. Now, when we compare that to the Nmap data, the hyperspectral data now, picking the exact same pixel, we can now see that there's a much better absorption feature here that's at 2165, has a much broader absorption. So if we compare that now to what we were seeing in the reference library for the alunite signature here, we can see how similar they are. Now, this is again the importance and highlighting why we should be interrogating the signatures. You can see how different the depths are of these signatures, right? The spectral library file is much more exaggerated, and that's because it's in the perfect conditions. You've got the perfect lighting, got the best setting with the right sensor with the most detail. You know, we're looking at this from space, and so there is a limitation on what we're going to be able to pick out, but actually we're going to be able to still see the key crucial absorption features that are allowing us to differentiate those. And then what we can do is take this absorption and then actually classify that. So we can actually see now that we've taken that absorption feature over the same location and rerun that absorption that as our input for our classification. So now I have a much more confident response of our classification that we're able to pick out, which is specific to the location that we're targeting there. It's always better to look at the geology that's relevant to the geochemistry of the region that we're targeting. And you know, that's one method that we can sort of go down, and by using the multispectral or some of these different hyperspectral classifications. Here's another one. I used our ternary image here to actually pick out a dykite signature. We've got two absorptions, one at 2167, one at 2173, I think it is, for the Nmap sensor, and then at 2208. So that same doublet that we're seeing here. And then you can see, again, the classification that we can do there. And then here as well, we have this sort of full workflow of an input porphyry signature, that porphyry characterization that came from the USGS classification. And you can actually see here, now we've got one high value up here, but actually two here as well, two sort of outcrops that actually overlap with where we were seeing the alunite and the dykite classifications take place. So I then took a spectral signature over this one area. You can see the sort of comparison here, and if we zoom in, you can see a sharp absorption at 2165 that's taking place there. Now, to me, this is where it gets a little bit muddy because it's not a perfect porphyry signature by any means. You can see how there's variation here and there's a secondary absorption here. And this is a function of what we call spectral mixing, right? We're dealing with a 30-meter pixel. There is more likely than not going to be one or more minerals present that are going to then factor into our absorption features. But what I can say, at least, is because of this sharp absorption that's taking place, there's likely to be some porphyry present that we can then target. Now, this is the best end member that I could find in the imagery, and so that's why it's being used in there. But once I feed that into the classification, you can see that there's a much smaller area, really only one of these original outcrops being detected from the imagery. So it does increase the confidence by taking those end members to be able to include that in there. And then from this, you know, we can take these different outputs and make sort of rough classification maps where we can incorporate where we see those overlaps. Some people like these, some people don't. It depends how you work in the field and want to operate. You know, we are ultimately still going to have some mixed pixels, and some of these will overlap on top of each other because they're going to be mixed compositions, but we can see where we're getting the strongest responses for these different compositions. So we have been able to pick these different minerals out here, which were also visible there. Now, the important part here was to now compare this with the airborne hyperspectral data sets as well. So you can see for each of the minerals that we picked out here, we've got alunite on the left here. We've got our original fused data set at the top. We've got our Nmap data, so our satellite hyperspectral there, and then our airborne hyperspectral at the bottom. Now you can see the improved sort of quality of the data, the sort of smoothness, and there's less noise along the far end here, which is only natural with an airborne system that's also flying at a much higher spatial resolution. But still, we're picking out those key diagnostic absorptions. With porphyry, you get a slightly better signature. There's less mixing because we've got a 4.5 meter pixel, 4.6 meter pixel compared to 30 meters. But actually what I found was the dykite signature in the Nmap data, so the satellite data, performed much better, and I could get a much stronger spectral response than from the HiMap data. Interesting, I'm not quite sure why that is. I might have to discuss with people afterwards, but it's good to look for. We can then compare these and actually look and say, well, was the Nmap data correlating with what the HiMap data was seeing. And despite the 30-meter pixel that we're seeing here, the main outcrops were still being picked out. Even the smaller ones are being more subtly picked out there. So, it's by no means a perfect correlation between the two, but the key areas that you're picking out are still being highlighted, even though it's, this is 3 or 4 pixels in size. It still would allow someone to be able to target the highest potential area for perophyllite being present. And the same goes for alunite. This is one of the limitations that I had with some of the data here. Because it had been masked already, I didn't have the sort of control to be able to mask out some of the data. And so you can see the area that had the highest alunite potential is actually pretty heavily masked. Now, I trust the interpreter of this data that was a realistic masking for what they were looking at. But because I would want to focus in on this data, I would like to have the actual unprocessed data myself. So maybe in future I'll be able to get that and be able to take a look in more detail. But what we can see at least is the rough same exposure is being picked out. And sorry, I forgot to change these. These are alunite at the bottom. And then what we can compare here is actually taking that multispectral signature. So if I fed that multispectral signature that we were looking at the start, how would that compare? And you can really see the difference there. That we see, roughly the outline of the outcrop of the hill being picked out, and there's highs in that same shared area. But there's a lot more being picked out there that are potential false positives that you can spend a lot of time walking around in the field looking for a certain mineral that may or may not be there. And so there's real value in being able to take the hyperspectral data to make sure that you're there. And then we can do some really fun things as well now, like compositional mapping. So we can look at where the biggest abundances are for white mica here, and then also look at the position of these absorption features. At lower white mica absorption features, it's typically a relatively aluminium-rich mica compared to at higher absorption features, which is relatively aluminium-poor. So you can see that there's some compositional variability there, and when we think about that in terms of the porphyry system, that could help us vector one direction or another. Unfortunately, at one porphyry it could be from low to high, and another porphyry it can be from high to low, but at least gives you a sense of a potential vector that you could look for. And we see this at a lot of big deposits around the world as well. This is at Reko in Pakistan, and the actual main deposit that's going to be mined out is up in the top left corner here, and you can actually see some of those vectors that helped the team there actually understand how to look for the center of that deposit. So just some takeaways now. We were able to identify several of the key minerals that we were looking for and identify compositional variability, but we're still limited by some of the spatial resolution. That 30 meters is going to limit what we're going to be able to do. But it may help you direct your next port of call, right? Is it worth going into the field and targeting some of these areas? Or is it where you start to look for investment in a higher spatial resolution from an airborne or a drone survey, for example? We could still look in, this is a relatively regolith-dominated terrain, and we're still able to pick things out pretty successfully. I mean, some of these are sort of a single pixel or two in size, so not large outcrops really in a remote sensing scale of things. But we could also improve this by sort of working backwards along that chart that I showed at the start. If we had field spectral data that we can use, or even drill core data, which I think is available over here, I just haven't got time to look into it, then that may help us refine that, because we can feed those spectral signatures that are directly related to the geochemistry of this area into our analysis and look there. I do want to just hark back to the importance of this and put this in perspective again, right? We have more missions coming that we're going to want to look for, but we also have a huge archive of data that we're growing and getting more of. Now, we're not the only ones working on this. CSIRO are doing an amazing job pulling together all of the spectral data over Australia and trying to make some different mineral composition maps from those. And the data sets are ever growing. Joe sent me this from July of this year, and now we're jumping to how much data they have as of August. So there's a huge amount of data that we can be pulling in and working with that across that to get analysis there. And the aim is to sort of have a single data layer that they can analyze different minerals to target there, which is amazing to work with. We're also trying to grow our hyperspectral archive. You can see our current coverage over Australia. We work with global mining companies, so we're also looking in some pretty crucial regions, and these just a couple of highlighted. You can see the amount in South America as well as the Western US. Now, we only ingest data based on interest from our clients, so you can sort of start to see where I think we can pick out all of the key critical mining districts in Australia there, but it's very easy for us to bring in any of those data sets. We have more than just satellite data coming as well. This is airborne data over the Western US. It's being collected by the USGS. At the moment, this is the current coverage as of today. I believe they're flying even more surveys this week. So the aim from 2025 is to fill in the rest of Nevada here. And then in the next couple of summers, they're going to be doing Idaho, Utah, New Mexico, Colorado, and bits of Wyoming as well. So they've got a lot of data that's going to be coming down the pipe at a much higher spatial and spectral resolution as well. So jumping down from 30 down to 15 and even 8 meters. And again, all of this is publicly available that we can analyze and access. The biggest challenge is how do you process it all? And again, we've got new commercial sensors coming down the pipe as well in the coming years. We're going to need to be able to analyze those and understand what the capabilities are, but also the limitations of these data sets. This is a real summary of the hyperspectral data sets that are available at the moment or coming down the line. And so it's really, really tough to be able to analyze these all together in a single place. And that's really what our platform is allowing users to do. So we can analyze and work with all of these different data sets in the same platform with the same tools and work with that seamlessly. And I'll sort of leave this running in the background or maybe wait for some questions. This is just a comparison in terms of the speed at which I can process a workflow compared to sort of typical remote sensing software that has been the traditional workflow. So I'm running one classification here on the left-hand side, and then you'll see the workflow that I'm building out on the right. And then I will stop here and take any questions. Thank you.